All right. What we're going to talk about today is really starting Chapter 8. We'll get pretty far through Chapter 8, I think. We're going to talk about stress. The first part of this course, you talked about a number of various things, but they all related to statics. So they're all related to the forces that act on bodies and finding the reaction forces that must act on bodies to keep a beam or whatever you were talking about, to keep it in equilibrium. You're still going to need to know that. You're still going to need to know how to find reactions, how to do all those good things that you did in the first 7-8 weeks of the course. But now we're going to start taking a look at sort of the inside of those bodies and what happens, to a member when you pull on it. Why does or doesn't that member snap in half? How much does that member stretch out? Why do some members stretch out more than others? So those are the things that we're going to start talking about. We're going to start talking about them in Chapter 8. And this really, for most people, this is a more, I'd say, practical part of the course, because you can start thinking about certain things that we talk about, and you can say, yeah, I know stuff in real life that acts that way. Whereas, when you're just talking about equilibrium, sometimes that's a little bit more abstract. You're talking about forces, and, support reactions, and you're trying to think, have I ever seen those before? And that's sometimes hard to grasp. But in this, this 6 week section, 6.5 week section of the course, there's going to be a lot of stuff that we see. The first concept that we'll talk about is the concept of stress. Okay? And again, starting off, we're going to talk about direct stress. Some people call this simple stress. But we're talking about maybe a stress that could be a tension stress, where we pull on a member. It could be a compression stress, where we push on a member. It could be some types of shear stress, where we try to rip or punch through a member. There's even a stress that we'll talk about that's called a bearing stress, where we have one member that sits upon or sits on top of another member, let's say. All right? So there's a lot of applications of the type of direct stress that we're going to talk about. What is stress? Just in general, what are we talking about? Well, what we're really talking about when we talk about stress, and it includes all these types of stress, but other types of stress as well too, is we're talking about the internal resistance that starts to build up in a member as it's acted upon by external forces. Okay? So what I like to start out thinking about, trying to teach people about stress, is think about this. Think about we're playing tug of war, and we've got a rope. Okay? And I have one team over here, and I got one team over here. All right? Now, what you've learned in the first 7 or 8 weeks of the course is the team over here is pushing or pulling on this rope. If they push on the rope, the game doesn't work too well. But if they pull on the rope, let's say the one team's pulling with 500 pounds of force. What you learned in the first 7 or 8 weeks of this term is that the other team on the other side, in order for there to be equilibrium, has to pull back with an equal amount of force. So if there's 500 pounds pulling this way, there's got to be 500 pounds pulling that way if there's equilibrium. Now, sooner or later, somebody wins, so you know, they pulled with a bigger force, okay? But here's what we're going to talk about. Why doesn't the rope break? Or maybe we could say, what happens internally to the rope so that it doesn't break? All right? That's what stress, this type of stress that we're talking about. There's other types of stresses. I mean, we'll talk about bending stress in beams. We'll talk about shear stress in beams. We'll talk about combined stress a little bit later on. There's other types of stresses, but for right now, we'll sort of limit it to this concept of direct stress. Okay? So, what is what is this stress all about? Well, let's start out by writing, the formula out, and I'll write the formula out in words, and then we'll write it out in symbols. Then we'll talk about what it means relative to this rope. So, the formula for stress is force divided by area. Okay? Now, the area that we're talking about here is what I would refer to as the area that's resisting the force. Okay? So always ask yourself when you're in a problem and maybe you're asked to determine what the stress is in the member, think about the area that's going to be resisting that force. Now again, if we're talking about the rope in tug of war, I think you'd have to tell me that that force is being resisted by the cross-sectional area of that member, right? Okay. So that force here, the big, 500 pounds or whatever we're pulling on it, it's got to be resisted by this cross-sectional area. So what is stress really? Well, stress would be saying if you took an incremental piece of area, let's say it's 1 square inch, how much force could act over that small piece of area? Okay? What differential amount of the big force is applied to incremental amounts of that area? Okay? So that's what, if you look at all these little pieces of area in this cross section, and you thought about the force that they all withstand, if you added up all those little forces over all those little incremental pieces of area, what would they total up to be? The total force. Okay? So all we're talking about is the total force divided by the, in this case, total cross-sectional area. Okay? What units do you think we have then? Well, if we're in U.S. units, you're going to have something like pounds divided by square inches. Or a lot of people call that PSI. You could have, in U.S. units, kips divided by square inches. People would shorthand that KSI. And you could have pounds per square foot. You could have kips per square foot. That's a little bit, that you'd have to be working on a bigger scale to see that. But, you could see that. If you're working in SI units, you're going to be dealing with pascals or kilopascals or megapascals. All right? Again, now, you're probably more familiar with the SI unit system than maybe I am, because maybe you grew up with it a little bit more. But in that case, the Pascal is really a Newton per square meter. So you're going to see, like when I do problems, I always make sure my area is in meters squared, because that makes it easy. Okay? And if it was a kilopascal, just make sure that it's a kilonewton per meter square. If it's a megapascal, And just make sure that, you know, it's a meganewton. Okay? That's the way I always think about this stuff. All right? Getting back to this stress, you know, over this cross-sectional load, over this cross-sectional area. In a rope, what you could think about in stress is, you know how rope is made up of all individual fibers? I mean, that's sort of what stress is. It's almost like saying, hey, what's the incremental amount of force, differential amount of force that's applied to each one of those strands? You know, so you have a, you know, 100,000 million little, you know, force vectors acting on each one of these little individual strands, and they all add up and they all combine to be the total force. Now, if this rope was going to break in half, what would happen? I mean, physically, what would happen? The individual strands would break, right? And why would they break? Because there'd be too much force on those individual strands. Or we would say, and this is the way we think of it because not everything we deal with is made up of individual strands, we'd say the stress that was on my member exceeded the material stress that it could take, the stress of the material. And here's where you get into strength of materials. You know, we don't spend a whole lot of time in this course talking about, oh, this material's this strong and this material's that strong. A lot of people think strength of materials is, you know, hey, you spend all your time talking about that. We don't really, we spend a little bit of time talking about it, not a whole lot, but, you know, the concept, whether this was rope, steel, concrete, wood, the concept would be the same. If this was going to break or if this was going to fail, it would fail because the stress got too hard. All right? Here's one of the most important things with this. You have to, right now, know the difference between stress and force. Okay? A lot of people will come out of this, I mean, if they're going to struggle with this, they'll never understand the difference between stress and force. And here's the difference. I mean, you already know the difference, I think. You should know. All right? But here's the difference. If I had a bridge cable on the suspension bridge downtown, and I said, hey, that bridge cable has to hold 500,000 pounds. Is that a lot of force or not? Is that bridge cable going to fail or not? What would you say? Huh? It depends. The right answer is it depends. I don't know how big the bridge cable is. I don't know, you know, what material it's made out of. 500,000 pounds sounds like a whole lot, but again, if I got 500,000 square inches of cable resisting it, 500,000 pounds divided by 500,000 square inches, that only gives me 1 psi. That doesn't sound like a very big amount of stress. So the correct answer actually is it depends. There is a difference, though, between force and stress. I mean, you need to know force, but force is just a big raw number. Okay, stress is really what's going to tell you whether a material fails or not.